artificial gauge fields with ultra-cold atoms in optical lattices.
Yes, hello everybody, and thank you for the invitation. I'm very happy to be here. I will be talking about my PhD work that I did in a group of Emmanuel Bloch in Munich. Currently, you can find me in Paris in a group of Jean Dalibar. And so what I will be presenting today is a slightly different approach to rotating Bose-Einstein condensates. So we were working on engineering artificial gauge fields in optical lattice potentials. And after all these nice talks about fractional quantum Hall physics, I will go one step back. So we are not quite there yet. We are working on it. But well, mainly I will not consider interactions at all during this talk. So it will be in the framework of single particle physics. And I'm trying to convince you that we can actually study similar physics related to integer quantum Hall effect in our cold atomic systems. And in particular, what we were interested in is measuring non-trivial Chern numbers, meaning Chern numbers that are not equal to 0 in artificially engineered energy bands with our cold atom optical lattices. And what I should also mention is that we are actually working with bosonic neutral atoms, not with fermions. So the talk will be as follows. I will first discuss the experimental setup that we are using. Then I will briefly summarize a few of our experimental results, just to give you an idea of what we can measure in our experimental setup. And the main talk will be then about the Chern number measurement in the presence of artificial magnetic fields. And just in the end, I want to mention a few words about what are the current challenges and what do we have to do in order to reach fractional quantum Hall, the limit of fractional quantum Hall-like physics. So as you have already heard, it's not as straightforward in our atom systems to study quantum Hall-like physics because our atoms are charge neutral and we cannot simply apply a magnetic field and study the related physics. But we have to engineer or develop other techniques in order to mimic those effects. And while you have heard, there have been many successful pioneering experiments exploiting the fact that the Coriolis force is equivalent to the Lorentz force. So if you set a gas into rotation, you can see these apprecursor vortex lattices appear in the Bose-Einstein condensate. And I've only mentioned a few works here, but you can look them up in many review papers. There have been many really beautiful experiments about rotation. But there are other ways in harmonic traps in order to engineer artificial magnetic fields by engineering spatially dependent optical couplings that are then mimicking Aharonov-Bohm phases in the quantum gas. And I will not discuss that here, but I think Ian Spielman will be in the workshop later, and if you want to know more about this, you can ask him. The idea of moving on to optical lattices was motivated by several proposals which have shown that in optical lattices maybe it's easier to reach the high field regime, which may make it easier to reach high filling factors in order to be able to study fractional quantum Hall-like physics. So this is what my talk today is going to be about. And also there has been a lot of progress during the recent years. There have been several techniques on how you can engineer artificial magnetic fields in optical lattices by off-resonant modulation, where we will hear in the talk by Tilman Esslinger how you can engineer or realize the Haldane model in honeycomb lattices with ultracold atoms. And even more recently, there has been ideas implemented where one of the two axes in an optical lattice is replaced by a synthetic dimension. So you use as a second axis instead of a real optical potential internal states of the atoms that are coupled by additional laser beams in order to engineer artificial magnetic fields. I will be talking about resonant laser-assisted tunneling, which is a bit similar to these ideas of off-resonant shaking, but by coupling two different vibrational states in the lattice. So a brief reminder about how our setup actually looks like. So we trap cold atoms into standing waves of optical laser light. And the lattice spacing is on the order of a micron, so it's much larger than typical solid-state setups. And we typically have around 10 to 30 lattice sites along one axis, and we can have 1D, 2D, or 3D optical lattices. Most of the work I will be talking about today is in two-dimensional optical lattices. And the motion of the neutral atoms in these optical lattices can be then described by the Hubbard model, bosonic or fermionic Hubbard model, depending on the species. But since I will neglect interactions, the Hubbard Hamiltonian here is very simple. We only have one spin component. There's no on-site interaction, and all the dynamics is simply governed by the tunnel coupling between neighboring sites, which is typically real. But this changes if we think about charged particles that are moving in this lattice potential in the presence of a magnetic field. Because there, the hopping matrix elements become complex. The particles pick up a phase that is essentially the Aharonov-Bohm phase. So it's related to the vector potential that is generating the magnetic field that is present in the system. And if you then think about a particle that tunnels around a closed loop in this lattice, it will pick up a finite phase that is related to the magnetic flux piercing one unit cell of the lattice. So all we need to do in our experiment is essentially to engineer complex hopping matrix element, which we can then interpret as a magnetic flux that is piercing the unit cell in the lattice. So how can we do that in our lab? I will explain it using a very simplified model, a double-well Hamiltonian. And all the techniques, we have studied several experimental setups, start with the same idea. So we apply a potential energy offset between neighboring sites, such that atoms cannot hop between neighboring sites. So this occurs if this energy offset is large enough to suppress tunneling. And then we apply an additional modulation potential, an additional time-dependent potential that shakes one lattice site periodically up and down with a frequency that is resonant with this energy offset. So then particles can absorb and re-emit photons from this field that is created by additional laser beams and hop to the neighboring site. So now if we apply this resonant modulation, there might be this additional phase factor. And now if this modulation is fast enough, we can apply Fouquet's theorem and compute an effective time-independent Hamiltonian. And there we see that now we have engineered a time-independent Hamiltonian that has a renormalized hopping matrix element between neighboring sites. And there's this complex factor which is related to the phase of the modulation that we have applied. So all we need to do if we can engineer this kind of time-dependent Hamiltonian is to make these phases vary across the lattice such that the particles pick up a finite phase when they perform a closed loop on the lattice. Yes?
So this phase phi is between two different oscillations, right? Or
yes.
It's an absolute phase?
Yes, so in this notation you could simply gauge away this phase. It doesn't have much meaning. But then if you look at two neighboring bonds, the relative phase between the two neighboring bonds is what matters.
Oh, so the phi is actually changing
across the lattice. So I will show that on the next slide, how we do that in a two-dimensional lattice. So it's slightly more complicated than that. Depending on the experimental parameters, you have to take into account that this Hamiltonian actually only describes the stroboscopic evolution of the system, but it doesn't tell you what happens within one driving period. So for analyzing the experimental data, one has to be careful about that. Okay, so how do we do that in a two-dimensional lattice? So it's the same idea. We apply a linear potential that introduces an energy offset between neighboring sites to inhibit tunneling along one direction. And there's normal hopping along the perpendicular direction. There's nothing going on there. And then we apply two additional laser beams, here shown in red, that are finely tuned to the atomic resonance. They have slightly different frequencies, where the frequency difference matches this energy offset. So these two beams, they interfere, and you have a running wave across the two-dimensional lattice. So this is what's indicated here with the gray area. And this is what introduces or restores the resonant hopping between neighboring sites, because now On each side, the local optical potential is time dependent, and it wiggles around with frequency omega and has a certain phase that varies linearly across the two-dimensional lattice. So this phase increases linearly along x and y. And what matters in the end, what sets the value of the flux that is penetrating one unit cell, is the projection of this wave vector difference on the y-axis. And then you have to compare the phase along this bond compared to this bond, because laser-assisted tunneling occurs only along the x direction, where we have the initial potential energy offset, but not along the y direction. So this is what sets the phase, which in principle simply depends on the geometry of the laser beams that you have chosen here. And using this technique, we can then realize the Hofstadter model, which is here complex hopping matrix elements along x, and phi is the flux that is penetrating one unit cell of the lattice. And there's real hopping along the y direction. Now, this technique has been implemented in our group in Munich and also at MIT in the group of Wolfgang and Ketele, and we will hear more from Markus Greiner tomorrow, I think, about actually tunable magnetic fields, I think. So by varying the angle between these two beams, you can engineer any magnetic flux penetrating the lattice as you want. And just to mention here, these fields that we engineer are very strong. They are on the order of 1 flux quantum per unit cell. So 1 flux quantum would be 2 pi. We have engineered a value of 1/4, and in the group of Wolfgang Ketele, it's 1/2. And just to mention, so this is independent of the internal structure of the atom, so you can apply it to bosons or fermions or different species. Here we are working with bosonic rubidium atoms. I skipped a lot of experimental challenges and details, so our final setup looks actually like this, which is a lot more complicated, but the essential idea is the same. There's one thing I also will mention later, that the complex phase that we engineer depends on the sign of the energy offset between neighboring sites, which actually allows us to engineer spin-dependent magnetic fields. Okay, so now a few experimental results that we have obtained with this lattice setup. One thing that we can study is using superlattice potentials, isolated ladder geometries. And why is that interesting? Well, so you can show that if you load or prepare the ground state in this ladder geometry in the presence of a magnetic field, there are chiral currents present along the legs of the ladder. So you have a current pointing upwards on the right leg and downwards on the left leg. And what we can do is we can measure these currents on the left and right leg of the ladder by projecting the ground state wave function onto this isolated double well potential. So now all the dynamics only occurs between two neighboring sites, and the amplitude of the current between two sides of the ground state wave function then is proportional to the amplitude of Josephson oscillations between these two neighboring sites. So by doing this measurement, we can extract the chiral current that is present around the ladder that we have prepared.
Sorry, are you talking about spin current or actual physical atom transport?
So it's a probability current. There's a phase gradient in the wave function, and this we can measure then in terms of. Yes. Yes. So it's the phase gradient that we measure. Yes. And by doing that, we can identify two different phases, which depend on the relative coupling between rung and lag. So K over J is the rung to lag coupling that we tune here. And we can identify phases similar to a type 2 superconductor, which are the vortex and the Meissner phase. And what's maybe more familiar for you to have in mind is if we plot this value of the chiral current as a function of the external flux that we apply through this ladder geometry. So if we increase the external flux, we are in the Meissner phase. There's a chiral current that screens the applied flux. And once we hit the critical value of a flux, it decreases, and we enter a vortex phase where this current around the ladder decreases, and we have vortices in this current pattern forming. Okay. Another experiment that we can do to measure more directly the strength of the artificial magnetic field that we have created is to isolate or partition our two-dimensional lattice in isolated four-side square plaquettes. And you should think about this now as really a single atom in a 4-side square plaquette, and this single atom is initially delocalized over this A and D sides. And what we want to look at is the dynamics after switching on the magnetic field. So first we prepare the atoms on this bond, then we suddenly switch on the magnetic field and let the atom tunnel to the right bond. Now, if there wouldn't be any magnetic field present, what we would expect that a single atom simply tunnels between the left and right bond. It undergoes Rabi oscillations, and that's all what's happening. But now, in the presence of the magnetic field, we see that there's this chiral-like motion. So it starts here on the left side, that's the initial state, at y0. So this is the mean position of the atom inside this 4-side square plaquette. Then it tunnels to the right, but instead of undergoing simple Rabi oscillations, which would be along this line, it gets deflected and performs this kind of orbit. And by fitting this dynamics, we can extract the value of the artificial magnetic field that we have engineered in this plaquette potential. And as a next step, I already mentioned that we can engineer spin-dependent magnetic fields. So making use of the fact that this complex hopping matrix element, the phase, or the sign of this complex hopping matrix element depends on the sign of this energy offset, we can make this, this artificial magnetic field spin-dependent by loading 2 internal states into our optical lattice that are 2 different Zeeman states with opposite magnetic moment. So if we create the linear potential using a magnetic field gradient, now the 2 spin components will see opposite potentials. And since they see opposite potentials, they will see complex hopping matrix element with different signs in front of the phase factor. And this will lead to fluxes that have the same strength but opposite direction. And this allowed us to observe the spin Hall effect in an optical lattice. So now the initial state, it's again the same system. It's a 4-side square plaquette. And we have prepared the single atom initially on the lower bond, and we let it tunnel to the upper bond in the presence of a magnetic field. Now, depending on the spin state, we get a non-trivial oscillation perpendicular to this initial tunneling direction, which is mirrored depending on at which spin state we are looking at. And now if we look at the oscillation amplitude of this non-trivial motion perpendicular to the initial tunneling direction, we will find that it depends linearly on the spin imbalance that we have prepared. So if 50% of the atoms are spin up and 50% are spin down, then we don't see any non-trivial oscillation along that direction because it fully cancels out. Okay, so this is so far about the experimental results that we have obtained in order to be sure that the artificial magnetic field that we have prepared is actually there. But what we are interested in is to study the topological properties of this system. So we wanted to measure the Chern number of the energy bands that we have engineered. And so how do we do that? So in the single particle framework, you can characterize the topology of an energy band in terms of its Chern number. So the Chern number is simply the integral over the Berry curvature of the first Brillouin zone. And the Berry curvature characterizes the topological geometry of the energy band. So U is the periodic Bloch function, and well, the Berry curvature tells you how the eigenstates evolve as a function of kx and ky in momentum space. And there have been several experiments trying to map out this Berry curvature in momentum space by interferometric measurements. So you can think about implementing an interferometer in momentum space by preparing a Bose-Einstein condensate at a certain position in momentum space. Then you perform a certain beam splitter, and you can perform the experiment by making a closed loop, for example, around the Distira cone and measure the pi flux associated with this Distira cone, which was done also in our group in Munich. And there have been other experiments about state tomography by really reconstructing the phase of the eigenstate and amplitude of the eigenstates and computing the Berry curvature. Here you can see a map of the Berry curvature in a graphene type lattice. This is kx and this is ky. This is for 2 different directions of the Berry curvature, and blue and red are different signs of the Berry curvature. Here the band was topologically trivial, so if you sum up the Berry curvature of the over the full Brillouin zone, you will end up with 0. But here you can see that in cold atom experiments, you can actually map out the full Berry curvature in the Brillouin zone. So all these experiments were done in cases where the Chern number of the band was trivial, and we now wanted to study a case where this is actually non-trivial and is larger than 0. Just a reminder about the Hofstadter model that we have realized. So we have complex hopping matrix elements along X, and we know that the single particle energy spectrum of this Hofstadter model is the famous Hofstadter butterfly. So depending on the magnetic flux that is piercing one unit cell, the lowest tight binding band splits into several subbands. In our case, we have realized a flux of 1/4, meaning that the magnetic unit cell that is now describing the translational invariance of the underlying lattice is 4 times larger than the original unit cell of the lattice, which tells you that the lowest tight binding band splits into 4 subbands. So this is the energy of the lowest tight binding band, and this is the flux that is piercing one unit cell in the lattice. And the lowest band here has a Chern number of 1 and is topologically equivalent to the lowest Landau level. Now if we go here to lower magnetic fields, we reach here the continuum limit where you see the Landau levels more or less equally spaced here in the lower part of the Hofstadter model. Okay, so what's the strategy of extracting the Chern number from our experimental measurements? So the idea is that we apply an external force to our atomic cloud. So we load a Bose-Einstein condensate in our optical lattice in the presence of artificial magnetic field, and then we apply an external force and look at the in situ dynamics of the cloud. So what do we expect to happen? If we look in semi-classical dynamics and we look at a wave packet that is prepared at a certain position in momentum space, we expect that in the presence of this external force, the atoms undergo Bloch oscillations in the direction of the force. And if the band is non-trivial, we also expect that there is an additional component which is perpendicular to the applied force and proportional to the Berry curvature at this position in momentum space. And there have been similar experiments in the Haldane model, which you will hear later today. So what we expect if we perform this experiment is that the atoms not only undergo Bloch oscillations in the direction of the force, but they also undergo a motion perpendicular to this force, which is proportional to the Berry curvature. Now, how can we extract this anomalous velocity component and not looking at the trivial dynamics of Bloch oscillations and so on? So we consider in this case a filled band, a filled lowest band, which can be prepared with fermions by setting the Fermi energy in a spectral gap. Or in our case, we consider bosons that have a temperature that's much larger than the bandwidth of the lowest energy band, and thereby filling each quasi-momentum state in the lattice. And if we have prepared such a system, then the contribution from the band velocity averages to 0 because of the symmetry of the band. And we are left with the non-trivial evolution perpendicular to the force, which if we compute the center of mass motion, is simply proportional to the Chern number of the band where we have prepared our particles in and proportional to the force. So this is, again, the definition of the Chern number where mu is the band index. So if we consider that we have prepared all the atoms in the lowest energy band, so this is the energy spectrum for the Hofstadter model of flux 1/4, then we expect that the atoms, if we apply the force, simply move perpendicular to the force, and from this linear motion, from this slope, we can extract the Chern number of the lowest Hofstadter band. Now, if we consider that there are also higher bands populated, we can rewrite our formula, and we will see that due to the higher band population, we would expect a motion that is reduced. So the slope of this linear motion is reduced by what we call the filling factor, which is computed by taking into account the relative band populations in the Hofstadter bands. Now, one thing I want to mention is, because it's one of the things that are rather tricky in cold atom experiments, is how to prepare the initial state. So we followed a scheme. So if you think about, we start with a square lattice without magnetic field, and we prepare our Bose-Einstein condensate in this lattice. Then when we switch on the magnetic field, the translational symmetry of the lattice is broken, and the lowest tight binding band splits into several subbands. So this is not very favorable if we want to have a good preparation, a good initial state preparation, where we know what's the final state our atoms will end up. So our strategy was to engineer a lattice with trivial topology, but with a unit cell that is equivalent to the final magnetic unit cell that we want to have. So we engineered a lattice which has a unit cell of with four non-equivalent sides, so it's 4 times larger as the normal unit cell, by introducing an energy offset on every other side along both directions. So now we have an energy offset along the x direction and the y direction, which leaves us with 4 non-equivalent sides in a unit cell, and therefore the lowest type binding band of the original lattice is split into 4 subbands. And then if we load the Bose-Einstein condensate into this lattice, we can prepare it at a certain momentum state here, so we will prepare it in the minimum of the band. And then we can hope that by crossing the topological phase transition, which occurs when we reduce this energy offset to 0 between neighboring sides, so we ramp down this little delta to 0, and at a certain point where the detuning in this case is equal to 2 times the hopping matrix element between neighboring sides, we cross the topological phase transition where the gaps in the spectrum close, and we can reach for delta equals 0, the Hofstadter model for flux 1/4. Now, if we think about a Bose-Einstein condensate that is initially prepared at a certain momentum state, we can hope that during this transition it will not see this gap closing point and end up in the lowest band of the Hofstadter model. So the idea was really to preserve the number of bands during the sequence, and this actually allows us also to measure the band populations in the end. Yes.
So I have 2 questions. First is that during this process you wish to keep the temperature somewhere in between the band gap. So distance between the new 2 equals -2 band and the new 1 equals -1 band, but larger than the width of the new 1 band.
Yes, so if we would do that fully adiabatic, like if we would really start with a condensate here at a certain momentum state and do this, follow this transition adiabatically, we would not end up with a temperature that is larger than the bandwidth of the lowest band. But since we have heating going on during this loading and we are actually not adiabatic, we end up with a temperature that is larger than the bandwidth of the lowest band. So this was our initial idea how to prepare it, but so we have heating present, so it's actually not adiabatic, not fully adiabatic.
So by the time it becomes goes to the last step, it's not a BEC anymore?
No, it's not. Okay, and this is our experimental result. So what we do is we measure the in situ position of the cloud for a certain direction of the magnetic field. Then we switch it around, and we subtract these 2 clouds that we have measured for opposite directions of the magnetic field. And we do that because we want to get rid of systematic shifts in the position, in the central position of the atomic cloud. And here we see that the forces applied along this direction, for a certain direction of the magnetic field, this is shown here in red, it moves to the left, and for the opposite it moves to the right. And this difference is really perpendicular to the applied force. And if we follow this evolution over time, we see that it's more or less linear up to a certain point. Here it already seems to deviate from this linear behavior. And the dashed line shows the ideal evolution that we would expect, but taking into account the finite filling factor, which would be ideally 1. But since we have higher band population, it deviates from 1, and we already expect a reduced evolution. We can also extract a value for the Chern number of the lowest band from this data, which is close to 1 and has a rather large error bar. And if we perform numerical simulations, which are shown here in green, we see that we do not expect a perfect linear behavior already for these timescales. So this is roughly 2 Bloch oscillation periods, but we expect that there are Landau-Zener transition going on during the dynamics, which cause atoms to be transferred to higher bands during the dynamics. So then if we look at longer timescales, we see that it really rapidly saturates. And if we turn around to the force, we see that systematically the same thing happens. So this evolution is simply mirrored because we have switched the direction of the force. And we see that if we switch off the magnetic flux or study staggered flux configuration where the band topology is trivial, then we don't see any non-trivial motion perpendicular to the force that we have applied. And if we compare this to numerical simulations, we see that this cannot be captured by Landau-Zener transitions to higher bands, but there's something else going on during this evolution. And in order to understand this a little bit better, we can track the population of the different Hofstadter bands during the evolution. So this is what is shown here. The black dots is the relative population of atoms in the highest Hofstadter bands. This one is in the middle band, and this one is, no, sorry, this is the lowest band, and this one is in the middle band. And if we compute this filling factor, which is ideally 1, we see that over the same time scale, it decreases to 0, where 0 means that all the Hofstadter bands are equally populated. So we reach an infinite temperature state where we would not expect any non-trivial motion perpendicular to the force.
How do you measure the population of the different bands?
Yes, so that's, I have shown you how we prepare the atoms in the Hofstadter bands. So if we reverse this sequence, if we ramp it back, so we apply again this energy offset between neighboring sites, then at a certain point where this energy offset is large enough, then the modulation we apply is off resonant. So then we can switch it off, we map it to a static lattice, and in the static lattice we can apply usual band mapping techniques to measure the band populations. So we try to map this time-dependent Hamiltonian onto the static lattice and then use usual techniques. So this we still need to understand in more detail what's causing the band population or the repopulation during our dynamics, which leads to the saturation of the evolution of the cloud. But we can incorporate it in our simple model and simply integrate over this filling factor to compute the evolution that transfers to the applied force. And if we do that, we can use again the Chern number of the lowest band as our only free parameter and fit this value, and then we get something that is very close to 1. So this is all consistent and we understand what's going on, but we still have to understand the heating rates. Yes?
So is there motion in the third direction, or that's not important?
Yes, so the third direction I completely left out so far. So we have actually roughly 100 atoms per site, and they are in a 1D gas. And so, well, there's probably no center of mass motion in this direction, but we think that the heating that we see is related to populating higher modes along the direction in this 1D gas. Okay, so with this I would like to conclude. I have shown you how we can create artificial magnetic fields in our optical lattice and how we can realize or engineer quantum spin Hall Hamiltonians. We have performed measurements of topological invariance actually in 1D and 2D, where today I was only talking about the Chern number measurement. And further work we did was in the direction of topological charge pumping. If you're interested, I can say more about that. But regarding the 2D Chern number measurement or extensions along the lines of measuring interesting topological many-body states, there are a few challenges that we have to overcome, is to understand heating rates in our lattices. Maybe we have to study other techniques in order to engineer artificial magnetic fields, which are more useful and have lower heating rates. This we don't know. We have a lot of ideas with the existing setup, what could be done in order to reduce the heating rates. Then we need to enter the strongly interacting regime, which is also not straightforward. We need state preparation techniques and detection techniques. But to be a bit more optimistic about that, I want to say that the Hofstadter model for flux 1/4 seems to be very promising in terms of energy gaps, in terms of that we can compare to existing models, meaning that we can compare to continuum wave functions, because the effect of the lattice potential doesn't seem to be too strong yet, but strong enough to maybe study interesting deviations from the continuum limit. And with all the new techniques that are now available in cold atom setups, we can hope to study many different observables and hopefully provide complementary information about getting a better understanding of all the different fractional quantum Hall states. And with this, I would like to thank the team that was involved on this during all the years. Especially, I want to thank Immanuel Bloch and Marco Satala. We were essentially the 2 PhD students in the lab during all this time. And of course, our theory collaborators, Jean Daliba, Nigel, Nathan, and Belen. and also the team around Eugene Demler, where we did a 1D SAC phase measurement. Thank you very much for your attention.
So when you're doing the band mapping from the topological phase back into the lattice, you have to jump the gap, right?
So you mean the gap closing point?
Yes.
Yes, so that's a bit of a problem, that there's the gap closing point during this ramp, but it's not the limiting factor right now. It's rather that on this time scale of the ramp, we still have heating going on. So it's not perfect, the band population measurement, but it seems to agree rather well with our experimental data of the in situ motion, so we think it's not too bad. But it's a good point. It's not negligible. Without ramping back to the static lattice? Well, since it's modulated, we would need to find a way to do band mapping using this time-dependent Hamiltonian and stay always on resonance. And, well, we didn't come up with a good idea how to do that. It's not as easy as the normal band mapping.
I'm interested in what you call heat. In these time-driven systems, it's
Yes.
hard to distinguish something which is kind of the coherent excitation from the incoherent excitation. And if you're to reverse the time sequence that you use in just the right way, maybe magically you can bring it back to the original state. Have you tried to do those kinds of things?
So you think what we're seeing might be coherent transfer?
Yeah.
Well, I don't think that's the case. Well, okay, we have Landau-Zener dynamics going on, but that's not the only thing. So we have collisions between the atoms. Actually, the interaction energy is not as negligible as I have tried to convince you. It's actually rather large compared to also to the band gap.
So what should matter is
So-
the smallest gaps in the system. So most of these experiments are done in tubes. Right?
Yes.
So you have no gap along that last direction.
Yes, so there we can populate a lot of final modes along this direction. So
even
what?
without interactions, you have much smaller gaps that come from that lack of
Yes.
design in that last direction.
Yes.
Could you just turn on an extra lattice direction?
Yes. Yes, we can, and we tried, but the problem is, so we tried very briefly. So we think that by switching on an additional lattice in a vertical direction and decreasing this number of final modes that we have available along this direction, that we can find a position in parameter space where the heating is smaller. But when we switch on this additional lattice, then our on-site interaction U in the Hubbard model is very large. It dominates everything. And then, well, we simply didn't know what to look at in the end.
But in a sense, that's what you want to do.
Yes, yeah, no, I agree. Yes.
So when you do this theoretical model to include the higher bands, so that you do it by Landau-Zener transfers, but that's presumably incoherent, right? Whereas you could imagine, like also somewhat related to what Nate was saying, that there could actually be some coherences or some coherent oscillations between the higher band population. So why do you think that this should be incoherent, just due to the interaction energy?
No, I don't think the Landau-Zener transfer is incoherent, but I think that due to the additional heating, because of atoms colliding, that in the end what we see is some incoherent distribution. But I'm not saying that the Landau-Zener transitions are incoherent. Like what you have seen in the simulations, there's this is just coherent. Well, no, it's actually done for fermions, but anyway. So I'm not saying the Landau-Zener transfer is incoherent.
But the curves that you show, is this coherent or incoherent?
Which curves? The simulations?
The Landau-Zener curves that include like this dynamic
The green-
changing band population.
The green numerical simulations? Well, well, it was done for fermions actually, but so the idea is you just populate every momentum state and then you track the evolution over time.
So I have actually a related question to this heating problem. You're constantly driving the system and you're basically hybridizing different bands and you go to some rotating more bouquet basis to do our physics. Is it possible actually to also simulate thermalization in these flow K bands?
So you mean,
Driving the system,
yes.
and we're exciting the system, we have to engineer some way to extract the entropy out of the system, but in this rotating vector, in this new flow K basis. So something that actually takes us from the higher band to the lower speed and at the
Well, but I'm not sure how to think about thermalization. So, I mean, we have this infinite Floquet spectra. So I'm always taking out only one representative spectrum. Let's say a one Floquet number. So if I think about thermalization, that from higher bands you reach lower energy states, then there's no limit. I mean, you can. Yeah.
Well, the answer to his question is yes, and you can think about it for K band, and I think that in studying it, and I think so yeah, it's possible. In fact, that's what it is. That's the origin of it.
But yeah, but due to this, I think what we reach is this infinite temperature state. No?
Well, within your time, I can
Yes.
But related question, my question is that what do you think is a realistic? Well, within the scheme,
Yes.
do you think it's realistic to get to a really a 2D systems where you have the strong interactions? I mean, or you have indicated that which worries me a little bit that you seem to say that you would have to choose, you go to different method. This seems to be reaching the limit of it.
No, I don't think so. So we are trying to also study different methods because there are some experimental limitations on this particular experiment where we have done these experiments. But I think that it should be possible. So if the picture we have in mind right now is correct, that by confining really in 2D, so not having these one-dimensional tubes on each side, that we can find a regime where the heating rates hopefully are small enough so that we can go to the strongly correlated regime. But of course, I don't have any. Well, I cannot give you any numbers or any experimental results about that. But we still believe it's possible.
Okay, last question.
So when we're talking about the ladder, does it makes sense to